So, hello. Are you guys hearing on the back? Okay. So, hello everyone. My name is André Fatala. I'm a research and development manager in Magazine Luiza. And today we are going to talk about product recommendation systems based on the graph database. Thank you. I will start talking a little bit about our company, Magazine Luiza. And I need to explain something here, that Magazine is not a paper magazine. It's just an old-fashioned way to name it stores in Brazil. Our company is 58 years old now and is one of the largest appliance retail chains in Brazil. It's focused in the middle and low-middle income classes there. And Magazine Luiza has more than 530 stores there, physical stores, 8 distribution centers, more than 23,000 employees, and one base with 23 million customers. And Magazine Luiza has a strong multi-channel strategy in Brazil. So, but we are here to talk about recommendation systems, and we just start developing Bobby, that's the name of our project, in the beginning of this year, after we realized that we can just get and grab a lot of information about another project that we released that is social commerce. The social commerce, we just able people to create and publish stores inside social networks like Facebook and Orkut. And people can choose up to 60 products and insert in their stores and publish it in these social networks. And we just came up with the idea of grab all this data, collect it, insert in the database, and try to identify some specific behaviors in this database. And for that, we just choose to do this using graphs. First of all, talking about recommendation systems, the main idea is that in Magazine Luiza, we have a huge inventory with more than 50,000 products, items, that when someone comes to our website, wants to buy something specifically, like a LED TV or a Blu-ray player. And we need to identify this behavior and try to help this specific user to reach their goal by trying to recommend this type of products. So, and in the recommender systems, the main idea is to provide information and items that like to be interest to a person. And that is our main goal with Bob. And here we are going to explain how we collect, store, do some queries, and analyze this data. And to collect and store this data, we chosen a graph database that is more natural way to think about how to store this type of behaviors, because we can get some object or things in nodes and create relationship between these things. So the idea is to get a person and create an edge to connect this person to a product using the action that the user did with this product, like viewed some product page about a LED TV or add the product to cart. That's why we use the graph database. So I don't know if you guys are familiar with graphs, but the main idea is to create the relationship between nodes by connecting ads. And now we're going to go deeper in the technology part, and Renato will introduce your graph stack.
So let's start talking about the technologies that we use. Our graph stack is based on open source technologies, and we use lots of languages, mainly Python and Java. Our graph database is Titan. Titan is developed and maintained by the Aurelius team. It's a company focused on graph products. Titan is open source and is free to use, even for commercial usage. So this is good for us. It's a distributed graph database, so it scales a lot. It can work up to 1 billion of edges in a graph. Titan is a vertex-centric graph database, so you always need a starting point to start the traversal on the graph. So it's basically for OLTP queries, and we'll talk about later global graph operations. And Titan has native integration with the Tinkerpop stack, so you can use any technology that is part of the Tinkerpop stack, such as Gremlin that we'll talk in the next slides. When working with Titan, you can choose a storage layer like HBase, Berkeley DB, or Cassandra. And in our case, we decided to go with Cassandra, mainly because we can have high availability without a single point of failure. So this is the main reason that we chose Cassandra over HBase. Also, Cassandra has elastic scalability. This is very important because we started with low traffic, and then with the loads going up, we just started adding more nodes to the cluster. Titan has a good caching layer, so it can speed up the queries, and has built-in replication. This is also very important. So I'm going to show you the flow. It's pretty simple. How do we store the user's data? Wherever there is an interaction of a user with a product on the website, the Magazine Luiza sends a request server-side to our API. This request is received by our Elastic Load Balancing and sent to one of the instances that are running our API. So each instance has a Titan graph running, and Titan gets these requests and saves the interactions on the storage layer. In graph rewards, our graph model is basically this. A person can create a session. This session is created in a channel, like a physical store or the website. So, because Magazine Luiza is a multi-channel company. And a session interacts with an item, with a product. And we built a scoring system for that here. So whenever a user views a product, we add 1 point to the score. When he adds a product to the cart, we add more 13 points. And when he buys the product, we add 31 points.
So, as Renato said, the idea of creating this graph and the points through the interactions is to try to identify the interest of our users in some specific product or category. And here we are going to explain how we are using the data collected to do recommendations in our website. And Magazine Luiza has around 15 million unique visitors per month, and something like 200 million page views per month. So that is the volume of the traffic that you need to handle with your system to write the interactions and to deliver some recommendations in reads on your Cassandra cluster. So we started create some base recommendations as you guys can see in a lot of e-commerce players like Amazon, Best Buy, Target, and these basic recommendations allow us to create some derivations in the type of recommendations that we are using in our website. So here we have like a diagram to explain some of these basic recommendations. One of those is the who viewed this item also viewed, and we get the Xbox 306 to explain. So when someone accesses the Xbox and after the next the page view is on the Xbox One, the GTA 5, a controller, or the PS3, and who bought this item also bought, something like someone can buy the Xbox and the game, the GTA, and a controller. We identify all those behaviors. Another type of the basic recommendation is bought after view some item. So the customer just see the Xbox, but choose the PS3. And here we start doing some derivations like the upsell. And when someone is inside viewing the Xbox 306, and we can say, hey, we have a new version now, is the Xbox One, why not to buy this product? And now we're going to talk about how to query the graphs to grab these recommendations.
So for graph traversals, we use a language called Gremlin. Is anyone here familiar with Gremlin? Oh, first time I see someone. So Gremlin is actually a Groovy domain-specific language designed for graph traversals. It's pretty easy to learn. It's extremely easy. It has a great community. This part is very important for us in our department. Whenever we are choosing a technology, we see if it has a good community so we can learn more. It sees that it's more stable language. Is another point. And this is part of the Tinkerpop stack. So it works with any database that implements the Blueprints API. So if we decide to move our database to Neo4j or NDB or any other graph database that works with Tinkerpop, we don't lose all of our scripts and everything that we made. So I'm going to show you now how easy Gremlin is to query the graph. This is a really small graph. For example, we have 6 vertices and a few edges connecting them. And we want to know which people view the product. And the product in question would be the first one on the left, that is the LED TV 42 inches. So translated to Gremlin, it would be like this, g.v4.inviewed. So explaining step by step. G is the graph instance that we have. V4 gets the starting point. Like I said, when working with Titan, we always need the starting point. And 4 would be the ID of this vertex. And then we get the incoming vertices with edge label viewed. So this query is pretty simple. It finishes here, and the rest of the graph isn't touched. So even if we had a huge graph with billions of edges, it would be pretty fast because we wouldn't touch the entire graph, only the starting point and what's around here. And now a slightly more complex example. It's still pretty easy. It's actually a base recommendation. We're going to get the products that were viewed after viewing the first one. So who viewed also viewed. Like the last example, we got the starting point, then the people who viewed this item, and after that, for each person, we get the outcoming vertices with edge label viewed. And if you see the second product, the LCD TV 42 inches, is touched by 2 different edges. So we could infer in a recommendation that this is a more relevant product and would be on the top of the list. This is a simple example. When working with in production, a product can have up to 500,000 connections, so we can get useful information. I'm going to show you now how do we manage to pre-process those recommendations. As I said, in production we have lots of edges, and this can't be calculated in real time. So we pre-process those base recommendations to use them later for creating the personalized ones. So once or twice a day, depends on the volume of traffic for each product. The Bob application dispatches a task to simple QA service, the SQS, with the product ID that must be processed. Whenever a spot instance is available, it gets the task from the QA and start calculating all those base recommendations. Who viewed, also viewed, who bought, also bought, and then create shortcuts between the vertices. Like product A, we create a shortcut edge to product B, like also viewed. And then when we need to get those recommendations, it's pretty fast. And all the logs that are produced in this process, we send later to S3 so we can analyze later.
So another type of approach that we are using our graph is to do some personalized emails. And here we have something really cool to say, because before we create the Bob, our CRM department is not able to do this type of emails on our e-commerce. So our goal is to bring our customers back to buy some product using the behavior that we get and stored. And for those emails, we just use some, actually we send some emails based on some behaviors that a product has price dropped. It's something really cool, because in Brazil, we saw a lot of players send emails with a coupon discount to bring the users back and buy a product. And we are able to just store the information, that the price that he sees when they came to our website, and after this, with the price of this product has a change, we can send the email and says, hey, now the product is cheaper, what do you think, come back and buy this product. Another one is abandoned product on cart. It's really used on the market, and visits many similar products when we can identify that some user want to buy a specific type of the TV, a 32-inch TV, and send an email with a lot of similar products and try to bring this user back to the website. So here we have the technical part.
Yeah. The architecture of the email sending, personalized email sending, is pretty much the same as the email pre-processing. And we developed a separate application for the email sending that is connected to Bob API, but it actually could be connected to any recommendation system. So whenever there's an interaction of a user and a product, the Bob API sends a notification to our mail manager saying, hey, this user is on the website and he's viewing a product. And it works like a ping to say to the mail manager, hey, the user is still on the website. So after about 24 hours, the mail manager gets those users that stopped navigating on the site and decides whether it should send a personalized email or not. He checks if the user has accepted to receive emails, if he has already received an email in the last few days, And if all conditions are satisfied, a task is then dispatched to the SQS containing the customer ID. And it stays in the queue until a spot instance gets this to process. The processing starts with deciding which email template is the best for this user, if it is a price drop email, a abandoned product on cart, or if it is an interest email. And then it goes to the Bob API and gets the products that are related to this recommendation. After that, it goes to Magazine Luiza's API to get the up-to-date price, title, and description, and image. It renders the email and then sends through Amazon SES, the Amazon simple email service. And again, all the logs are then synced to Amazon S3.
At this point, we see how to collect it and how we use them to query in the graphs to do recommendations. And one so important part that we have is the idea to provide to our business department to get information about our users inside this graph and use to do some type of actions based on our strategy in the business. So after start the recommendations, we just sit down and think about, hey, we need to provide this type of analytics inside this graph and to provide the e-commerce to find some good things inside our graphs. And here we start using Faunus, and Renato is going to explain this.
Yeah, I told you earlier that Titan needs to have a starting point and is used for OLTP queries and not for global graph analytics or global graph operations. So when you need to traverse the entire graph, remember that Titan and Faunus are designed to work with huge graphs. So billion edge graph that can fit in the memory of a single machine. So when you need to traverse the entire graph, we use a tool called Faunus. Faunus actually works on top of Hadoop. I'd say that it would be something like Hive for graphs. And so it provides the input and output formats to work with our graph. We can import a graph from Neo4j and then do something and set the output format to Titan. This is very cool. And it runs on top of Hadoop that I think on the BDT track everyone is familiar with. And in this case, we use the Amazon EMR for that. So I'm going to show a very simple example again. So we want to know the average age of all vertices with all people on the graph. That would be all vertices with element type equals to person. And the script in Gremlin would be like this. When we execute this query, it's sent to Faunus. Faunus convert this to map-reduce functions that are later run on the EMR. And then it comes back with the result and presents to the user. So this is pretty easy because you don't have to worry about much about the EMR, about configuring the map and reduce functions. This is very easy, and it can run processing in very, very large graphs with small results. I'm going to say about our backup process that we actually use the Node2Snapshot utility of Cassandra. So every night we run Node2Snapshot on all machines of the cluster, and then we get the result and send to Amazon S3. And whenever it's needed, we just get from the bucket and run the recover utility. This is the big picture of our infrastructure. Fatal is going to explain you now.
Yeah, as you guys can see, it's not rocket science. You use some service from AWS that now you are able to do this type of recommendations. we are using the EC2, the SQS, the less cache, S3 for logs, and we are using a spot instance without scaling. That's pretty cool for us because we can consume all the masses in SQS really quickly. And our cluster, our customer cluster, using the EC2 largest instance that we have in Brazil. So, unfortunately, we don't have SSD instance or clusters in our region yet. So, as Renato says, with Faunus, we can run huge queries inside our graphs, and now you know a lot more about our graph, and we have some metrics, like we have 0.43 million Magazine Luiza identifiers customers, more than 50,000 nodes of products, 9 million total nodes, 350,000 million of total ads, and we stored until now 700 gigas of data since July, when you just launched our recommendation systems in production. And we already have peaks of 20,000 reads per second in the customer cluster. So, and we know that result matters, and before the Bob, our website using another solution, a huge player in the market, and I'm not going to say the name. And we compare these two solutions a lot since March, and we get some really cool results, like our time to respond for a recommendation is 10 times faster than this huge guy. And we reduce the cost of our recommendation solution in 6%. And we've compared that the fee that we need to pay to the player. So, and here we have a really cool graph with a revenue of just of the recommendations. And here in the last December, we started doing recommendations in Magazine Luiza website with the solution A. In March, our first Bob tests, just doing some recommendations in some slots in the website. And unfortunately, in May, we need to turn off the Bob for 2 weeks, and we can see the results in the revenue about the recommendations. It's pretty cool for us, because we need to just to prove in our company that we have a really good product, and we need to take the place of the solution A, the huge guy. And in September, Bob take place in our website based on the results that we get, compare the slots of the recommendations. And here is the final results. We increase in 190% the revenue of recommendations inside our website, changing the solutions. So, and here we have our next steps that we have to work with Bob.
Yeah, so the first thing that we want to do in the next step that we're taking is use Faunus to pre-process the recommendations, remove all that architecture of spot instances, because in our benchmarks, pre-processing all the products at the same time using Faunus and Hadoop is actually faster than keep processing this on demand. So we could process twice a day in about 1 hour all the products. We want to use some algorithms to identify communities in the graph. This is a very cool thing that we didn't started yet. And we want to replicate our Cassandra cluster to another region. So if there's a problem with the Brazilian region, we can just change the endpoints to the US. So we could use this for a disaster recovery plan.
So that's it. If you guys have some questions, there is a microphone in the aisle here. And thank you.